Okay, so today we will finish off our look at some spectrum analysis. Last week where we ended, we spoke about the use of the DFT and the FFT in terms of getting useful information from signals. And one of the things that we spent some time on was the question of the sampling window, that when you're looking at a signal, it's not just a simple question of taking the samples and doing the analysis. You have to be very careful when you take the samples, because if you suddenly start to take the sampling and then suddenly end, that sudden start, end on beginning and end creates high frequency components in the signal that causes aliasing. Right, and we spoke about that, and we saw that the alternative or the solution for it, it wasn't a perfect solution, but what we do is to implement some things called sampling windows, where you start the sampling gradually, then ramp up to a maximum level, and then you decrease it gradually back down to zero instead of the sudden start and stop. And we looked at a couple of them, and we saw that the main characteristics with the sampling window is that first off, you wanted to start close to zero and end at close to zero. And then the spectrum for the sampling window, you wanted to have, because they're not, of course, they are not ideal. So the spectrum for it is not a nice wideband spectrum. But what you want is that the main part of the spectrum is to be as wide as possible. And any additional parts of the spectrum, which we call the side lobes, have to be as close as to zero as possible. And we looked at some examples. Of course, we compared all to the rectangular window that we know from before, the sinc function. And we looked at the triangle window, and we looked at the Hamming window, and then two others, which was the Blackman and the Blackman-Harris. I just gave you the information, and then I told you that you can, it's possible to exploit in something like MATLAB, using their what they call the window designer tools. So you could play around with it and see what the responses and so on look like. All right. So today we're going to look and conclude with two other little tools that we use when you're dealing with spectrum analysis to help us in particular situations. And from an introductory level, that is good enough. As you get more involved in this or more advanced in it, there are many more techniques that are available for people to use as well, right? Just a little aside, some people have been asking me about things like a past paper question for the midterm and so on. If you do problem set 1 and 2 on the in-class examples that we did on the FFT, right? If you attempt those and you look at the problem sets and so on, then you're covering the material for the midterm. The question paper will come based on those kind of questions, right? With slight variation, right? So it's not like a big final exam where you have a lot of things to deal with. It's going to be an open book exam in class. You're going to have 90 minutes to do the questions and give me back up the answer at the end of the time. All right. So don't worry about that. Do the work. On Wednesday morning, the first part of the class, we'll have the tutorial on problem set 2 and answer any little questions there, and then we go ahead again after that. All right. So don't sweat it. All right. So one of the things that you meet, right? What we've been dealing with so far, and probably through all your career in engineering, are signals where the frequency content doesn't vary with time. In a general term, we call those signals stationary signals, right? So the frequency content is not varying with time. But there are certain types of signals, for instance, speech or musical notes, to give an example, where the spectrum or the frequency content is time variable. So in other words, if you look at the spectrum at time 0, and then you look at the spectrum at time 10, let's say, the spectra are different. Same thing for musical notes. Those types of signals in a broad sense, we call non-stationary signals. All right. And just to know that in the rigorous definition of it, whether signals are stationary or non-stationary, and they call it stationarity, right, really involves how this signal behaves statistically, not only the frequency content. And if you're doing your comms courses, especially in the advanced comms courses, or if you're going to do postgraduate work, you're going to meet these a lot. All right. But for our purposes, if I tell you a signal is stationary, what does it mean? The thing is that the frequency content doesn't vary with time. If it's non-stationary, like speech or like music, then the content signals, the frequency content, the spectrum is going to change with time. So the problem is, if you have something looking like what I'm showing there on the screen, where the frequency content is varying with time, so at here, early on here, for instance, you have fairly low frequencies, but up here in this zone, somewhere here now, right, you have what appears to be a lot of high frequency information. And then if you look at here, you could see that there's some low frequency variation here, but there's also high frequency variation going on top of that. How do you go about analyzing a signal with that using the fast Fourier transform or doing spectrum analysis? Well, we take a very engineering approach to it. What we do is to look at the signal one part at a time. So again, if I were to make an analogy, if I were to give you, like in the early days, give you something like this and tell you, well, where's the gradient of that? Well, clearly the gradient is varying with time. And the approach that we took was in your calculus was to take a section here and assume that the gradient was a straight line. Then from here to here, you assume that the gradient was a straight line. Here to here, you assume that the gradient was a straight line. Here to here, you assume so and so. So you had a series of gradients for each of these points, straight line calculations, and then you found a way to add them up together, and this came up to the whole concept of finding the derivative and so on. We take the same very practical approach to analyzing non-stationary signals. What you do is that you take the non-stationary signal and you look at the frequency content a little bit at a time. And you use something called a sliding time window. Each part now, each time window, and remember the time window is what we spoke about last week, Wednesday. So each part now, you get up, in other words, you take this, the entire signal, and you split it up into smaller chunks. And each of the chunks, you apply the FFT to that bit, and you get the frequency content for that little part. And then you go on to the next bit, and you look at the frequency content of it. So you slide, you start, and then you slide the window or move the window to another part of the signal, and then you repeat until you cover the entire signal, okay? This approach is something called a short time Fourier transform of the signal. It is not a new transform. What you're basically doing is applying the FFT to short intervals of the signal itself, okay? And because you're doing that, they call it a short time Fourier transform of the signal. So how it works is that here's the same speech signal that we had before. So I start with a time window, a sliding window, a sampling window, which is the part that is showing in gray there. So the whole signal looks like it's going on for, let's say, about 4,000 milliseconds, right, in duration, up to here, right? There's a little over 4,000 milliseconds. So what I do, I take a chunk. This is looking like about, 750 is here. So you're probably looking at about 800. So we take a 800 millisecond window of the signal. And for this thing, for this 800 milliseconds, we do the FFT on this. So it is FFT1. And then we slide the window and we keep going in chunks of 800 milliseconds until we finish the whole thing. So we're going to have a FFT1, an FFT2, an FFT3, and so on. All right. And so for each window, notice that the size of the window has its own number of samples now. Right? I said I was talking in terms of time, but remember that the sampling, if you know your sampling frequency, right, and you know the time that you're taking here for your sample, then between these two, you can know how many samples you're going to take. So that's the size of your window in samples. And for each of those bits, you on the FFT. All right. So at the end of the day, each result going to have time, frequency, and amplitude characteristics. When you do the FFT, right, the FFT has frequency and amplitude, right? So there's an amplitude here, and there's a frequency component, but this entire thing took place at T1. Right, or interval T1, whatever you have it. So as you slide it around, you have three things that you're dealing with. You're having time, you're having frequency, and you have an amplitude. For each of the time slots, you have an amplitude and a frequency response to deal with, right? And you could display each of them separately. So what I could do, I could say, okay, for interval T1, and I could look at what the spectrum looks like, interval T2, or we can combine them all into one thing, a special figure that we call a spectrogram, right? The amplitude, the spectrogram, typically the axes are time and frequency, and we show the amplitude with color. So it's an image, right? It's really an image, it's not a plot. So we have time on one axis, frequency on the other, and the intensity of the frequency spectrum, we are going to code in color. So you're really creating a picture. And this is what the spectrogram looks like. For instance, that speech image that we that we had early on. So you have the time. So time is going along here. Frequency is going along here. And now this is the intensity here. This may be most likely in decibels. So, of course, you will define the scale. So the higher the number, the higher the amplitude, the darker, the closer to red it is, the lower the amplitude, the closer to blue it is. So you can see from here, right, all of the high frequency, or the frequencies with high levels, you can see them in areas like this, okay? And then the frequencies with low levels, which would be like these sort of colors and so on, you're seeing them in between here. So it's a picture. So you take the non-stationary signal, and for each of them, for each time, you did a spectrum, and you combine everything together to create this image that we call a spectrogram. So for instance, if I look at look at what happens. I have time and frequency here. So if I take a slice in this direction here, what this is going to show me is that for a fixed frequency, whatever that value is, for that particular frequency, let's say this one is somewhere around 2300 Hertz, right? It is going to show me how that 2300 Hertz signal varies with amplitude as I go along time, from 0 to, in this case, what, about 0.5 seconds kind of thing. Everybody seeing that? So if I take a frequency and go horizontally, in this case, for that particular frequency, I will see how the amplitude of that frequency alone varied. If I go this way and look at a particular time, well, my line is a little crooked, but if you look at the particular time here, then at that time, I could see how the spectrum of the signal looked. So if I go up here, this now is telling me at this time, the signal had whatever the spectrum, high frequency components, low frequency components, and so on. So a slice along the time axis shows how a single frequency varies with time. A slice along, sorry, yes, a slice along going a long time at a single frequency shows how the frequency varies with time. A slice along the frequency axis gives me how at a particular time, how the spectrum of the signal looked like. Make sense? Here's another little version of it, right? This here, X and Y is relative because sometimes, depending on the software, depending on how people do it for convenience, they sometimes put the time on this axis and the frequency here. All right, but you understand, is it making sense what I'm talking about here? Yeah, everybody following? Right, so this now allows us to do, for instance, things like voice print analysis. So, and you could try it, and you'll probably do it in one of the problem sets. For instance, you record your voice saying a particular word. And if you run the spectrogram, this is the kind of things that you have. So for instance, the one on the, both of these are the same, or is the same word spoken by two different people. And this is how you can use, well, we have voice analysis here, but this is how you can also use systems to detect one voice as against another. Or you can tell if somebody is imitating someone else's voice, right? You could sound exactly the same to your ear, but when you look at the actual spectrogram of the particular spoken word, you will see a lot of, there will be differences in it. All of these have to do with how the voice is modulated and so on. And it's a huge range. It's a huge application in audio processing, and especially in things now like with voice recognition and artificial intelligence and machine learning and so on, where they would take this sort of information and have the system or the device or whatever it is learn how to distinguish one voice from another. Okay, but it all comes back down to starting off by recording the information, which is non-stationary, performing this short time Fourier transform of it, which is to slice it up into bits and pieces, do a spectrum of each slice, and combine it into one image, which is called the spectrogram. And then you could code that now into whatever it is that you want to apply this for. Okay, so among the things that we could do, so once you do that, one of the things is that you have to be careful about the particular window that you use. Of course, you can't use a rectangular window. And you remember why? Right, so you're taking the stationary, the non-stationary signal, and you're using the sliding windows, but you don't want to use a rectangular window. Anybody remember why? Right, it creates discontinuities, and discontinuities do what to a spectrum? Because everything here is boiling down to a spectrum, frequency information. Right, it creates high frequency components, so you get aliasing being created, because if you create high frequency components, what you're going to do is to create signals that were not there before. So you're going to have the entire thing is going to be messed up. So what you want to do is to use any of the other of the many sampling windows that are available, as for instance, a Hamming window or the Blackman or all of the others. There are many windows around. Most times, the most general purpose one is the Hamming window. And in fact, it's so general purpose, even devices like Arduino and Raspberry Pis and so on have Hamming window codes already as part of the library, so you can call it just like you would call a regular function. You could call that and have it done. It's so common. All right. So the window size is in terms of samples is capital N subscript W, because we distinguishing it from the overall length of the particular signal in terms of samples, right? And you select, you remember you're moving one window and you're sliding the window. After you've taken this, you slide the window down to another point. And what you do is that you select the windows so that they overlap to get better coverage. Typically half of the width of the window, right? So this is what you're trying to do. When you remember, if you were to, let me just go back to the original picture here. So if I had this here, so I'm covering from here to here, right? So if after I do that now, I slide my window down to here, right? Then, so this is the next set I'm looking. If I'm not careful, I'm going to miss this set of information inside of here. So when you're doing the windows, what you want to do is to actually overlap the windows so that you don't get any gaps missing, right? You know, you don't omit unintentionally omit data that is good, that should be part of the spectrogram. So the windows are typically overlapped. And what you do is that you overlap it typically about half the window size. So if I pick, let's say I'm dealing with a window of size 512 samples. Remember, again, because we're using the FFT, the size of the windows has to be 2 to the power of some number. All right. So if the window size is 512, for instance, then the overlap typically is 256, half of that. It depends on the window lab, but a window type, but usually most people use an overlap of about half. And if you do that, you get this sort of behavior here. So the light blue here is the first window. The sort of purple one here is the second one. And because we overlap it by half, you notice that you don't, you sort of double count some people, but more importantly is that you're not omitting anyone. All right, and then you slide it along again by half, and then so as you do it, you get an overall picture of what the spectrum will look like, and you're not omitting any set of values inside of there. All right. Remember a little issue as well, though, is that if I had originally n samples in my whole signal, and I sampled by I sampled at some frequency fs, then the original resolution was fs over n. Yeah, but I am taking a subset of that because the signal is non-stationary. I am actually taking less samples than the original set that were in the signal before. Because I'm taking less samples, the resolution here is bigger. In other words, the sliding window will pick up less frequency components, or to use a jargon that we have been speaking about the last couple of weeks, has less bins than the original FFT on the whole signal. All right? But you're trying to solve a thing. You can't run the FFT on the whole signal because the spectrum is varying. So you have to subdivide it. And in doing so, your resolution has gotten a bit worse. So again, it's always a compromise. All right? The frequency resolution has been decreased. The time resolution has been increased because we sort of zoom in. We've zoomed into the signal time by dividing it up into smaller chunks, but by doing that we have reduced the frequency resolution somewhat. Okay, and like many things, and because we sort of use it all the time, MATLAB has a spectrogram function exactly like this. So what you do is that you give it a number of data. You could tell it, if I were to just end it at spectrogram X, then it would automatically, there's a fallback. It would look at the signal that you have, how many, first off, how many data points you have in there, and to run an FFT on it, it would pick 2 to the power n and divide it up according to its own algorithm. It will pick its own values inside of it to give you the spectrogram. If you want to be more specific, then what you can do, you can tell it what window you want. Here I have Blackman, or you could put Hamming, right? Then you have to tell it the size of the window, how many samples you want. You have to tell it how much to overlap. As I said, the overlap is approximately half. Well, it's not approximately, it's half the size typically of whatever you choose for the window size, right? This now, I noticed that in the later versions of MATLAB, you don't need to tell it the FFT size. Once you tell it this number here, it automatically will do an FFT of that size for you. Okay, and then you tell it the sampling frequency that you're using. That determines when it plots it out for you, it will plot the frequency components accurately for you. If you don't tell it FS, then what you would get, instead of let me go back here. Yeah, instead of frequency on this axis, what it would give you is something called normalized frequency in radians, right? Because you're not telling it a sampling frequency, it will just normalize everything in terms of radians. And you will have to divide that by your sampling frequency. Of course, you remember omega, you remember omega is equal to omega TS, or 2 pi F over Fs. So if you don't give it this, it will plot this instead, and you have to now do the manual calculation to get it into Hertz. All right? But again, I'm not, it's not something I'm going to examine you on here, but it's something that we will meet in the problem sets and so on, right? Because I can't ask you how to, I can't give you this to do in the exam and so on. It's how to get it done, but I need you to understand how the spectrogram works. So everybody it makes sense? Yeah? Right. The other way that we use spectrum analysis sometimes to help us out is that it may be better when we have the spectrum to determine signal power instead of just the signal amplitude. Now, if you remember, signal power is really proportional to the square of the signal amplitude. And we use signal power a lot, for instance, in communication systems. You're always interested in how much, for instance, how much power is in a particular frequency band. And as I mentioned before, people like the Telecoms Authority in Trinidad are very strict about how much power is used in a particular band. And if you're licensed to use a particular frequency band or particular part of the spectrum, you are constrained by how much power you could pump out. All right, that's part of your license. Luckily for us, there's a theorem called Parseval's theorem. We're not going into it here, but essentially, Parseval's theorem tells us that the energy in a signal in time, that the total energy in a signal summed across all the time is actually equal to the total energy of its spectrum summed across the frequency. In other words, the energy in time is equal to the energy in frequency, which, if you think about it, is kind of common sense. I mean, it's just a different way of looking at the same artifact. We have a signal, We could look at it in time, or we could look at it in frequency. But the energy of the signal can't change. You can't create or destroy energy. So the Parseval's theorem, I mean, the proof is a little more complex than this, but what we're interested in is a result that if I want to find out how much energy is in a signal, I could do this, which is hard to do, because how am I going to integrate a signal, a continuous time integral over the signal and so on? But if I know that this average, this power is the same as in the spectrum, then the power in the frequency domain is the same. So then let me get the spectrum and get the power from there, because I know I could get the spectrum. I could get the spectrum of my signal here by using the DFT or FFT, right? So I take the signal XT, right? I sample it to get XN. And if I transform it now to get the spectrum, the energy or the power in the what do you call it, spectrum is the same as what I had in time, so that I could work with that. And this is something I could compute mechanically, right? I don't have any what do you call it, continuous time integral to evaluate, right? This particular version, right, where you determine the power or the total energy in the I'm kind of interchanging power and energy. Remember, power is really energy by time, right? So we could work around that. The energy of the spectrum, right? If I take the signal, sample it, and then run the Fourier transform and basically add up all of the energy in all of the spectral components that I get. And remember, how I do that is basically to square the magnitude of it. So like when you're working with voltages and you want to find out how much energy you're dissipating in something, is V squared over R, for instance, in a resistor, that kind of thing. Same thing here. So you square it. That particular expression is known as the spectral density of the signal. All right. Density, again, you remember density from your sort of physics is like a mass over volume. So basically what you're doing is you're taking you're taking the energy in each particular frequency component and you're summing up everybody, right? And the average of that now, so if you take all of these and you add up all of them, you get something called the spectral density. And if you average that now over the total number of points that you have, you get something called the power spectral density, or PSD, of the signal. So remember, we started with XT, we sample it and we get XN. From XN, we get XK. We square XK, add up all of them, right? Add up all of them and average it over the number of frequency components that we have, and we call that the power spectral density of the signal, right? You may have come across that term already in your comms courses. I'm sure you have, somewhere, because it's something that the comms people talk about a lot, right? And we can use the FFT now to give us an estimate of that, and we call that particular use of the FFT a periodogram. So what the periodogram does is that it evaluates this for us. When you take this signal, you do an FFT of it, you get all the XKs, you square them, and then you average it over N, and you create something called a periodogram of the signal, or the power spectral density of it. How useful is that? Well, of course, okay, just a little aside, you can do this in something like MATLAB, Again, the same process, just like we had with the spectrogram. You give it the data, you give it the window. Remember, you always use a window, no, not rectangular. I'll talk about this in a second. You tell it the FFT size. As I said, in newer versions of MATLAB, once you pick this number, this is automatically sort of selected for you. And you have to tell it your sampling frequency. Now look how that helps us. The one above was one that we did last week. This is a signal. This is a 1,000 hertz signal or 1 kilohertz signal. We sampled at 7 kilohertz. Notice because the bin spacing didn't coincide with the 1 kilohertz that we have a lot of leakage. So we're supposed to get a spike here, but the nearest bin spacing is at 875. And then because you get leakage, you're getting all of these other components here. We tried putting windows on it, it doesn't work and so on. But if I were to take this signal and run as do the periodogram on it, in other words, look at the power spectral density of this signal on top. Look at what happens below here. It is telling me that all of the power in this signal is really concentrated in one frequency component. The rest are negligible. Right? So this, the periodogram on something like this is giving me a much clearer picture. What I could say here is that this definitely has one frequency component. Right? Everything here is negligible. So this signal most likely has one frequency component. What it can't tell me is that it's a 1 kilohertz. It will tell me because I'm only using 8 samples. So this is telling me that I have one frequency component at 875 hertz. Right? But this is better than this one. The straight FFT spectrum is telling me that I may have one component, but then wait a minute, there's another biggish one looking here, because this is a third the amplitude of that one. And this one is about a quarter the amplitude. So I'm not quite too sure yet, you know. But by doing a PSD or power spectral density on it, you're going to get this sort of behavior here where, because you're looking at the power in a particular signal component, clearly if the signal only has one component, the PSD is going to show you that as a main as a main contributor to whatever the result is. And all the rest are almost, well, here's 0, and here's as close to 0 as you want. All right? So that's the sort of application of it. Make sense? Yeah. So what we did, right, in terms of spectral analysis, last time we saw that, okay, we can do an FFT now. So once you want to do the FFT to create a spectrum, you have to do some little, you have to be careful with it. You need something called a sampling window. And the sampling window has some characteristics. Having done that now, you can get your spectrum and do whatever analysis you want. If the signal itself, however, is a particular type of signal where the frequency component is varying with time, we're dealing with something called a non-stationary signal, then we need to do something special to that. And what we do is to divide the signal up into time. And in doing that up, doing it into time and then plotting the spectrum as the spectrum varies with time, we create something called a spectrogram. The spectrogram is an image that on one axis will show you time, the other axis frequency, and the individual levels will show by color inside of there. Okay? And then on the other side now, for back to the signals that we have, if you're dealing with particular signals, another way of analyzing the signal is by looking at the power spectrum of the signal. So instead of looking at the regular spectrum that we had before, we look at something called the power spectrum and create something called the power spectral density of it. And because you're dealing with power, then for signals where, like the example that we have, where you have leakage taking place and you can't really distinguish one component from the other, and what may be the real component and what may be noise and so on. If you look at the power spectrum of the particular signal, it very clearly shows you if you have one component, all of the power going to be inside of there. And it now makes it easier to distinguish from the real signal from the signals that really are artifacts of the processing or produced because of leakage and other processing issues that may be around. Yeah? Make sense? Right, so first part was a continuous time Fourier sorry, not a continuous time, a short time Fourier transform that leads to the spectrogram. That's for the non-stationary signals. And then back to our stationary signals now. If you look at the signal, if you look at a signal and the normal spectrum is not, that you get is not allowing you to distinguish between the components adequately, you could then look at the power spectrum of it, look at the power spectral density of the particular signal by basically squaring the frequency content and averaging it out. And then that now gives you, in some cases, a much clearer picture of what the actual spectrum was. Okay, so two things that we covered there. All right. So your takeaway from this is of course, one, what is a stationary versus a non-stationary signal? If you have to apply or get a spectrum of a non-stationary signal, how do I do it? And the other part is that if I have a signal where, because of leakage, it's difficult for me to detect the actual components of the signal, what can I do? Well, the takeaway from that is that instead of looking at the signal at the raw magnitude levels, what I could look is to look at the power spectrum of the signal and see where the power in the signal is actually residing. And that now will allow me to get a clearer picture into what the actual components of the signal are. All right. Okay, so any questions on that? We good? All right, so Wednesday morning, please go to the first half of the class. We will talk about problem set 2. We'll run through the answers for that. And then the second half of the class, we'll do a quick review of Z transforms, because we're going into some transform and some filter designs later on, but just to refresh your minds on what the Z transform is about. All right, not so much now how to get the Z transform and so on, but what it was about, because that is how the transfer functions for like filters and so on that we will be coming up to talk about. That is how they are implemented, right? They're defined in terms of Z. So what this whole Z transform business was about, okay? All right, so I'll end the recording.